In this video, we're going to review the laws of exponents that we learned last year. So let's begin talking about exponents and the laws in general. Remember, any number raised to a power means that I repeat that number that many times, and I keep multiplying it together. So x to the fifth would be x times x times x times x times x. So when we begin to look at actual numbers, well, 3 to the first power would just be 3. 3 to the second power would be 3 times 3, which is 9. 3 to the third power would be 3 times 3 times 3, which is going to be 27. And 3 to the fourth power would be 3 times 3 times 3 times 3, which would give me 81. So if I begin to trace back, in this case, 81 divided by 3 would give me 27. 27 divided by 3 would give me 9. 9 divided by 3 would give me 3. So this pattern is important, that anytime I go up in exponent, I multiply by 3. Whenever I go down, I divide by 3. So using this principle, when we begin to look at saying what 3 to a 0 power is, or the 0 power, I would continue this pattern of saying, okay, 3 to the 0 power would be 3 to the first divided by 3. What's 3 divided by 3? It's going to be 1. And this is going to be my first important principle, or my first law of exponent, that anything raised to the 0 power is going to equal 1. Okay, you'll notice the exponent does not become 1. The whole entire phrase x to the 0 power would become 1. And then continuing on, if I begin getting into negative exponents, so I'm continuing to lower the value of the exponent by 1. So I go 4, 3, 2, 1, 0, negative 1, negative 2, negative 3, negative 4. Continuing this idea of dividing by 3, I'm going to take the 1, divide by 3, and in other words, it becomes 1/3. Continuing the idea another step, divide by 3. If I take 1/3 and I divide by 3, that's going to be the same thing as multiplying by 1/3. I end up with 1 to the 1/9, or 1/3 squared. 3 to the third power, 1/9 times 1/3. Okay, 1/9 divided by 3, keep change flip, becomes 1 to the 27th power. Well, isn't that 1/3 cubed? And 1/3, or 3 to the negative fourth, will be 1/3 to the positive fourth power. This gives me my second rule, that the fact that if I have x raised to a negative exponent, it becomes 1/x raised to the positive version of that exponent. And kind of keeping the same idea, 1/x to a negative exponent will give me the positive version of that exponent up top, over 1. Reason being, 1/x to the negative a becomes 1/x to the a. So if I keep this, turn this into division, 1 divided by 1/x to the a, let me change that to 1/1, it becomes 1/1 times, keep change flip, which would give me back that x to the a power. So these are the two rules that are fundamental to laws of exponents at the very beginning. Moving on to some of the laws for multiplication. If I have something raised to a certain power times something raised to a different power, I just need to add those powers. So an example of that would be x squared times x to the third. You'll notice that they have to have the same base. So I would have x times x for the x squared, and then for the x cubed, it's 3 more x's leaving me with a total of x to the 5th, which I get from doing x to the 2 plus the 3. If, however, I take the same idea and have a power raised to a power, this is when I'm going to multiply the powers together. For example, if I have x squared raised to the 3rd power, well, x squared raised to the 3rd power, doesn't that mean I have x squared times x squared times x squared? Since this here, the x squared, is what's inside parentheses, and saying I have 3 of those, I have 1, 2, 3. Well, that in turn gives me x to the 6th power. Now a caution, just as a reminder. If I have x squared plus x squared, okay, I'm going to end up with 2x squared. That I combine those, but since I'm treating it as how many of these items, like counting these numbers of items, I'm not multiplying. This rule, the rule of addition still applies to this. With laws of exponents, I'm mainly talking about multiplication, and I'm talking about division. Moving on to division. We're in number 5 for a rule. Kind of using the same idea, x to a power over x raised to a power. I can subtract those powers. One way of thinking about this is, let's suppose I rewrite this as x to the a times x to the negative b. Keep in mind, if it's positive, if it's negative on top, okay, or in the numerator, something like x to the negative b, the x to the negative b becomes 1 over x to the b. It returns to the bottom. Well then, using my laws of exponents that I just proved, it'd be x to the a plus the negative b, or a minus b. That I subtract those exponents. This one makes sense because if I had x to the 3rd power over x squared, wouldn't it be x times x over x times x? Well, what happens? 2 of the x's would cancel out, leave me with just x. Well, isn't that x to the 3 minus 2? One caution with this is if I were to reverse these, x squared over x to the 3rd, think about, where do I have more x's? Well, if I was to subtract them, be x to the 2 minus 3, which would be x to the negative 1, which would become 1 over x. Another way of thinking about this, instead of rewriting them, is just to think, well, I've got 3 x's down the bottom and 2 on top. Where do I have more x's? I have an extra x on the bottom, which is what would give me this answer. Okay. The 6th rule of exponent operates a lot like the last one, that if I have something raised to a power over something raised to a power being squared or being raised to a power, I have to multiply both those exponents by whatever I have on top. So let's say these are different numbers. Okay. So what that would mean is if I have x to the 3rd over, let's make that y to the 6th being squared, once again I would repeat that and I would end up with x to the 6th over y to the 12th. Okay. Just a cautionary note, the same thing would happen with multiplication. If I have something raised to an exponent and something raised to an exponent, all raised to the exponent, I would in a sense distribute that exponent, x to the AC, y to the BC. Okay, where this comes into play is particularly if I have coefficient like 2x to the 3rd raised to the 4th power. Keep in mind this is really saying 2x to the 3rd times 2x to the 3rd times 2x to the 3rd times 2x to the 3rd. So in other words, I would have 2 times 2 times 2 times 2, which would be 16, x to the third 4 times, so it becomes x to the 12th. One way of getting around this is to, in a sense, distribute that 4, okay, to both exponents, keeping in mind that the 2 really has an exponent of 1. So it's 2 to the first, x to the third, all raised to the 4th power. So it's 2 to the 1 times 4 times x to the 3 times 4. So it would give me 2 to the 4th times x to the 12th. And just for a review, it's okay if you want to leave it as 2 to the 4th, or you can change it to 16. Either's fairly accessible. If you can do that easily, it's worthwhile to probably go ahead and do it. But if it requires thought, or you don't know it off the top of your head, or involves using a calculator, you can usually skip that step. So hopefully this has been a helpful review. We'll continue to work on this the next couple days in class, but just wanted to do this as a quick refresher. You should be familiar from last year, but like many things, you may have forgotten about some of these rules. So hopefully this would make sense, and this is what we'll be working on.